This is a video for AQA Further Pure Mathematics. Calculus 5.4, where we're looking at integration using substitutions of x equal to tan u. We should already have met the ideas that 1 over 1 plus x squared dx as an integral is equal to arc tan x. Sec squared u being 1 plus tan squared is one of the trigonometric identities that you will have met, and the derivative of tan u being sec squared u is also something that should have been covered already. So these lead us to the idea that if we've got integrals that have got 1 plus x squared in them, then the substitution x equals tan u could be useful in solving these. So and remember that if x equals tan u, then u is equal to arctan of x. This could be written as tan to the minus 1 of x if you wish. So we're going to look at a couple of integrals now where we're using this idea of a substitution of x is equal to tan u. So here's one to start off with then. We can see we've got 1 plus x squared in the bracket there, so a good idea might be to say that let x equal tan u, and if we do that we can differentiate to give dx by du is equal to sec squared u. This is a definite integral with x values from 0 up to x equal to 1. So therefore we need to also work out the limits. When x is equal to 0, then we've got tan u is equal to 0, so u must also be equal to 0. And when x is equal to 1, then we've got tan u equals 1, and that gives us u is tan to the minus 1 of 1, which of course is pi by 4. Remember that you're working in radians. So we can make all of this substitution now into our original integral, and we can see that we get now an integral from 0 to pi by 4. So these are now the limits using u. We've got 1 over 1 plus x squared will become 1 plus tan squared of u, and that's the power 3 over 2. And then the derivative dx, we're going to make the substitution sec squared u du. So there's everything substituted in, but of course 1 plus tan squared is equal to sec squared, so 1 plus tan squared u to the power 3 over 2 must be equal to sec squared u to the power 3 over 2, or in other words, sec to the power 3 of u. So in total we've got sec squared u on the top line, sec squared u, and on the denominator sec cubed u, integrated between 0 and pi by 4. Well, that gives us 1 over sec, and 1 over sec of course is the same as cosine. So this is the integral from 0 to pi by 4 of cos u du. Integrating cosine gives sine, so we're evaluating sine u between 0 and pi by 4. Notice that we've changed the limits to be u, values of u, so there's no need to go back into a function of x. So we now have sine pi by 4, which is 1 over root 2 or root 2 over 2, whichever you prefer, 1 over root 2, minus sine 0, which is 0, and therefore our answer is 1 over root 2, which is the same as root 2 over 2. There's the full solution, and let's look at it on a neat version, just go through it again. So we recognized that we've got 1 plus tan squared here, so that our substitution x equals tan u might well be useful. When you make the substitution, remember that you've got to change the limits, so these are now limits for u. And also this idea, we've got to remember to look at dx by du. So we end up with a simple integral of cos u, which becomes sine u, to give us 1 over root 2. Remember that if you're using a calculator, make sure 1, it's in radian mode, and 2, it's set so that you get answers as surds. Well, as a second example, I've got this one here, which is 3x plus 2 over x squared plus 1 dx. Now, there are several ways of doing this. One way, for example, would be to split this into the integral of 3x over x squared plus 1 dx plus the integral of 2 over x squared plus 1 dx. And then you could use your standard methods. So this one here is a standard integral using arctan. And this one here, you can see that we've got, in essence, the derivative on the top line of the function that's on the bottom line. So it's going to be a log of x squared plus 1. But let's say that you hadn't managed to spot that idea, but what you did realize was that the function here contained 1 plus x squared, and so you decided that you wanted to use the substitution x equals tan u, which you know might be useful in these cases. So using that then, if x is equal to tan u, then dx by du, as before, is equal to sec squared u. So we can now make the substitution. The top line of that is going to be 3x, so that's 3 tan u plus 2, and the bottom line being 1 plus tan squared, or tan squared the way it's written, tan squared u plus 1. And then we must multiply by sec squared u du. Now it all looks quite complicated to start with, but we realize that 1 plus tan squared is equal to sec squared, so that those will cancel out, leaving us with 3 tan u plus 2 du. Now both of these are then very straightforward, because the integral of tan u is log sec u. So we get here 3 natural log of sec u, and then plus 2u, and of course plus a constant of integration. Now what we need to do is to look at the function of u here and change it back into a function of x. Well, if sec u is going to be equal to the square root of 1 plus tan squared u, so that's the square root of 1 plus x squared. So when we put that into the integral, we've got a square root of the logarithm of 1 plus x squared. Well, we can take the square root as a fraction out of the logarithm, so 3 over 2, and then inside the logarithm just 1 plus x squared. 2u, u is equal to arctan x, so this is 2 arctan x, and then plus a constant. So here it is written out for you. So remember that we spotted the x squared plus 1 there and said, well, let's use x equals tan u, see what happens. when you do that, most things are going to cancel out. Remember that you've got to do the derivative. Dx by du is sec squared u, so that when you replace dx, it's sec squared u du. And we get down to 3 tan u plus 2 to integrate at this point here. The sec u, when we're doing the back substitution, sec u was equal to the square root of 1 plus tan squared u. So that's the square root of 1 plus x squared. So we can write that as being equal to 1 plus x squared to the power of half. And then the part of the fraction there, the 2, represents that square root coming out of the natural logarithm. The other thing you could check is that this is the same result as if you'd split the integral into 3x over x squared plus 1 and 2 over x squared plus 1. So that the first part, the logarithm, there is the 3 over 2 log of 1 plus x squared, and the second part gives us the 2 arc tan x. So as I say, always going to be, or quite often going to be, several different ways of tackling the same integral. So we've seen that integrals involving 1 plus x squared can often be transformed using x equals tan u. And then, of course, we might end up with something where we have to use other techniques to finish off the integral. And do remember that when you've got definite integrals, changing the variables from x to u should be done, and then you simply use those new limits in calculating the value of the definite integral. That's the end of this particular video, and then there's another one looking at substitutions of a sine u and a tan u.